in the previous 2 chapters of the course, we looked at X, a scheme, and then we saw there's some nice extra structure that you can put on it in the form of sheaves of modules, and in particular quasi-coherent sheaves on this scheme. And we saw that they satisfy that on an affine open spec R, they are given by a sheaf associated to some R module M. And below, we can now give a particularly nice example of such quasi-coherent sheaves, which connect a local property of varieties, namely smoothness, to a local property of quasi-coherent sheaves that we have seen in the last chapter, namely of being locally free. And the idea here is, if X is, say, a smooth variety like this, and we have an open subset, then a tangent field on this open subset should be a nice collection of vectors in these tangent spaces, which fit together, which vary algebraically with the point inside this open subset U. And this should give us a nice sheaf of modules on X, because we can take a vector field and also multiply it with a function, getting a new vector field. So there should be an underlying OX module, which we can call the tangent sheaf. And the idea here is that locally around each point, kind of X looks pretty similar. We can basically write down a basis of these of this tangent sheaf, so basis of the tangent vectors, which makes this in fact a locally free sheaf of rank given by just a dimension of X, because that's how many degrees of freedom we have locally. So this is the idea that we have. But to make this precise, our strategy will actually be to first define not the tangent sheaf, but the cotangent sheaf, because this is kind of closer to something which we already know, namely to the functions on X. And then once we define the cotangent sheaf, which works for arbitrary varieties X over K, we can define Tx to be just a dual sheaf. So this is also some nice application of taking this dual, simply because, I mean, the tangent space at any point is the dual of the cotangent space. And since we expect this thing to be quasi-coherent, it should have a particularly nice form when X is just spec R, when X is an affine scheme, because then it should just come from some module. And basically in this video now, we're going to just write down what this module is. And this is already the next definition. So if R is a K algebra, so here we always work now over a fixed field K, then we define a module called omega R, and it is given by the quotient of a very simple module named just a free module, the free R module, with generators given by just all the functions f inside R. So here you take the direct sum of these, and then you have R times a symbol, which is called df, where d stands for kind of differential. So this would be a very, very large module like this, and these df's would be the generators. And then we divide out some relations. And here, this df should really be thought of as kind of this differential of f, and then we have some idea how this differential should behave. Namely, the differential of a sum of functions should be the sum of the corresponding differentials. And so this formal symbol here, d of f plus g, should be the same as the sum of these formal symbols here for all f, g, and r. Then the differential also satisfies a product rule, which is also called the Leibniz rule. Namely, d of f times g should be f times dg plus g times df. This is kind of the product rule that you also know for taking differentials of functions, again for f, g, and r. And then finally, we know that kind of constant functions should have zero differential. The constants here in this algebra will just be the things coming from K, from this field. And so we say that the differential of any element of the field should be 0. These are all the relations we divide out. So in other words, we take the submodule generated by the differences of the two sides in these equations and just divide it out. And then we get an R module, and this is called the R module of scalar differentials, or just the R module of differentials of R. And this, of course, depends on this K, so sometimes also called this differential of R over K. And we just observe for now that there is a nice K-linear map, which goes from R to omega R, takes this F, and just associates to it this formal symbol. And the fact that this is K-linear follows by combining the first equality with basically, well, with the second one, knowing that the differential of an element of K is 0. Okay, because this means that if F is in K, then D of F times G is F times dG plus 0, because the dF vanishes. And this differential map is a kind of curious map because it goes between these two R modules, but it is not R linear. Exactly the failure of being R linear. So if there wasn't this second term, then it would say that this is R linear, right? That you can just pull out the F. But the fact that there's still the second term here means it's not in general R linear. Okay, so we did write down an R module. And the idea here is that if you now on spec R take the sheaf associated to this R module, this will give you the cotangent sheaf on spec R. Maybe for how to think about this, if F is a function, just think about it in terms of these differential forms that you might have seen in analysis lectures. So if F is a function, then dF is a differential form. If you evaluate it at a certain point, it lands in the cotangent space of x at this point. And if you want to explain these rules, you should just think that if you now have a vector, a tangent vector to x at the point P, then pairing these two, so this is in the cotangent space, this is a tangent space, so you can pair them, you get a number. And this pairing here should give you the derivative of the function f along this vector v. So I think, I mean, this, we don't really make this precise what that this really all works in this context, but this is what you should have in mind if you want to understand all of these rules here, for example. Okay, so this was the abstract module. And now if we want this to fit together nicely on these geometric objects like these spectra, then we need to understand what happens when you, for example, restrict to an affine, distinguished affine set, or when you restrict to the stalk at that point. And these are both examples of localization on the algebra side. And so we need to understand what happens when we have a ring R and then we localize it. What is the relationship between the omega of the localization and omega of the original space? And we can do this very general. So if S in R is a multiplicatively closed subset, then we know we can localize at the subset. And so in the localization, we will then have elements of the form some element of R divided by some element of S. And then when we take this sheaf of, or this module of differentials, of scalar differentials, then we will get some symbols like D of G divided by F. And so we should understand what these things are. And there is a very simple trick we can do. Namely, let's say we want to understand what is D of 1 over F. Well, the thing that we know is that, well, 1 over F times F is 1, is a constant. And so its differential vanishes. This is one side. So here we use this third relation. But then also we know what the differential should do to products. And if we expand this, then we just get 1 over F times dF plus F times d1 over F. And then the idea is we can just solve this equation here for this D of 1 over F. And if we do this, then we get that this is just, so somehow we bring this to the other side. This gives us minus 1 over f df. And then we need to divide by the f. And so we get that this is minus 1 over f squared times df. Now, this is, of course, just the same thing as the quotient rule for differentials. And more generally, if we then multiply here by g times 1 over f, and use the product rule again, we can just check that the differential of such a quotient is just again given by the quotient rule for differentials. So it's just the same formula that we are used to. And all of these equalities, so all of these things make sense in this omega of the localization when the g, the numerator, is an arbitrary element of R and the denominator is an element of S. Just somehow we didn't really cheat at any point here. We just used the properties that we are allowed to use. And then the claim is from this we can write down an isomorphism from the sheaf of differentials on this localization to the localization of this R module at the element S. And for writing this thing down as an isomorphism of modules over this localization, we just need to say what does it do on these symbols which generate it, so on these d of g over f. And well, this just tells us what it does. It just sends this to the rule that we have decided. And here you see somehow this expression combines coefficients, which are elements in S inverse of R, with these module elements, dg and df, which are elements of omega R. So this is a legal operation, and and you can check that this is an isomorphism indeed, which just means that forming this module of differentials commutes with localization. We can first localize and form this module, or we can first form the module, getting omega R, and then localize at this idea. And that's very useful, and we're going to apply it just now in a second in the following claim. So now we start going to these sheaves. So here you have this R module, and then you get a sheaf on spec R just by putting the tilde over it. And the claim is there is a map of sheaves which is given by this differential. And here it's really important, is a map of sheaves of K algebras, if you want, or just of abelian groups, but it's not a map of OX modules. This is basically the same reason that this here is not an R linear map, but just a K linear map. And I mean, the proof is just very short. So somehow, how do you go from a function to an element of this tilde thing? Well, if you start with phi in O spec R on some open set U, then by definition, this thing is given by a compatible collection of elements in the stalks, right? So this is in phi p in RP, p in U. So somehow elements of these stalks, and the condition is that phi p is equal to g divided by f locally. And then, well, where could you send this under this map D? So this map D sends it to a section of this tilde sheaf, but this tilde sheaf is just a collection of elements in the localizations of these modules fitting together nicely, right? And so what you can just do is you can take just D of this symbol. And this, a priori, this lives in omega of RP, right? Phi p is in RP, and so this D of phi p lives in omega RP. But we have just seen, somehow this was the thing above, is that this is the same thing as the localization of, of omega R at P. And I mean, this is at least the right data, So somehow a collection of elements in the localizations of this omega r at the various points. This is the right data for being an element in this tilde thing on U. The only thing we need to check is that locally, this is given by the quotient of a module element here by a function in which doesn't vanish at any of these points. But this now just follows from this rule. If phi p is this locally, then this d phi p is given by just a formula f g minus g df divided by f squared locally. And this is exactly the right form to be a section of this thing here. And this already concludes the proof. So somehow we can write down such a map of differentials between these things. Okay. So this was all pretty abstract, just writing these abstract generators, relations, and so on. But now we can actually see what does this definition give us on examples that we know. And the most easy example is that just this polynomial ring over a field in n variables. And here the claim is that just from the rules, from these three compatibility or from these three possible relations, you can show that for any polynomial f like this, we have that this symbol df can be written as a linear combinations of the symbols dxi for the coordinate functions. And the coefficients are just exactly the partial derivatives of f along these functions. I mean, this formula looks pretty plausible, right? This is how you would compute an absolute differential of a function. And the claim is just that the three rules that we have allow you to do this. So for example, instead of giving a proof, let's just see it in an example. Let's say f is of this form, just 2x1 plus x2 squared. And then we want to compute this symbol here. Then we just use the linearity, to pull it apart into, to pull the sum apart like this. And then in the first term, we can use 2 as a constant. It comes from the field, so we can draw it outside like this. And in the second term, we use the product rule, which gives us x2 dx2 plus x2 dx2. In this case, it's not so interesting. And then we recombine this. You see here, this gives us the 2 times x2 times this dx2. And here we get just the constant 2 times dx1. But then we see, so we have written this thing as a sum of elements of these dxi. And the coefficients here, 2 and 2x2, these are exactly the partial derivatives of this polynomial along x1 and along x2. And so at least in this example, the formula is correct. And you can just imagine if you have an arbitrarily complicated polynomial, you just apply these sum and product rules as many times as necessary to, well, basically just calculate this total differential. And then you see that exactly the only things that remain once you have no longer any product is just some monomial of degree 1, so somehow just these coordinate functions, and the coefficients that you got in these rules are exactly the partial derivatives. Okay, so for this ring, even though we started with these infinitely many possible generators, these infinitely many symbols df, we could actually use the relations to write everything in terms of the dxi. And the claim is here that there's no further relation. So this is as far as you can go. So and the reason for this is that these relations here imply all the defining relations of omega r. So somehow if you impose these, then you can recover the three defining relations. And so these systems of relations are equivalent. And they give everything. And so somehow what this just shows is any element of omega r can then be written as uniquely as a sum of these some function times dxi. And so this means that this omega r in this case is actually a free R module of rank n, which is already encouraging because we expect that this is an n, I mean, the spectrum of this is an n-dimensional space, and so its cotangent bundle we expect maybe should also have rank n. So in this simple case, this was true. And then the next more interesting case is if we ask for some equations. If inside this this affine space, which has this as a coordinate ring, we impose some extra conditions. So if X is an affine variety, then we know its coordinate ring is given by this quotient here. And this relation here is still true. So somehow you can still apply all these rules whenever you have any function represented by some polynomial. You can still express it in these terms. And this just shows that omega r for this new r is still generated by all these dxi. But it will not in general be this free module, but you will have extra relations. And the extra relations just come from the fact that in this ring, of course, by definition, all elements f in I of x give you the zero function on x. And so, and they vanish inside this quotient thing. And so if you take that differential, then this is just the zero. I mean, this is literally zero inside this ring. And so d of this must be zero. Just because f is the zero function in this ring. And so these things give additional relations. And you can again show that what this means is that this omega r is still generated by dxi. So this is what you get if you just use these relations here. And then if you use these extra relations, what you just see is that in fact you can just take any generating set of this ideal, so f1 up to fm, and then the corresponding relations d fi is equal to 0. If you expand them, then you get these things, these equations, and this is in fact sufficient. So you just impose these extra conditions, and then you're good. So somehow this omega r will be a quotient of this free R module by finitely many elements, like this. And this has the nice property that now we can relate it back to this concept of cotangent space that we have already seen. Namely, let's say we have P, a maximal ideal in R. This should correspond to a point in the affine variety X. Then we have seen that we can take this this sheaf, I guess here, maybe this should be a tilde over here. So you have this sheaf on spec R, and then you can take its fiber at the point P. And by definition, the fiber here we saw can be just calculated by such a tensor product over R with this R modulo P, like this K. Since this is maximal, this is actually isomorphic to K. And so what you do is you take this quotient here and you tensor it over R with K. What then just happens is that all this direct sum with coefficients R becomes a direct sum with coefficients K. And what happens with these things is that, I mean, tensoring with K, with this particular isomorphism of R modulo P to K, just means that you take these functions and you just evaluate them at the point P. This gives you elements in K, the partial derivatives of these polynomials at this point. And then this just becomes this quotient here. Okay, but this thing, so somehow you have n copies of K and you divide out by all of these formal symbols here for the generators of your ideal. This we have seen back in the days when we talked about tangent spaces. This is just one presentation of the cotangent space of X at the point P. And so, okay, what did we do here? We constructed this sheaf on spec R and showed that the fiber of this sheaf at the point P is just a cotangent space of X at the point P. And that's a good sign that we are on the right track to defining the cotangent space. It certainly has now, in a very canonical way, the correct fibers at all the points. And this motivates why this is the right thing to consider. So this was everything about what happens on the level of an affine scheme. And the next thing that we will have to do now that we understand kind of what happens on spec R is we need to find a definition which also gives us this thing for an arbitrary scheme X. And this will be the task of the next video.